Recording is rolling. It is Tuesday, April 8th. Today's mostly going to be a lab day. I have a few demos and puzzle questions for you guys leading into this, and then show you guys how we're going to round out this week. Okay, so a lot of things going on. Okay, before we get too far, guys, you should have a bunch of materials on your desk, including a stack of magnets. That's one of the materials. You guys see a stack of magnets? Here, guys, safety thing. Are you guys going to put these magnets anywhere near your cell phone? The answer is no. Are you guys going to put these magnets anywhere near your laptop? The answer is also no. Because what happens if you suppose this was my cell phone right here? Or how about this? If this was my cell phone, I take the magnets and I do this with it. What happens? It wipes all the memory. Wipes all the memory. Yeah, which is probably not ideal. You don't do that. Right. So get that out of the way. All right, let's hit. Here, I got a James Burke puzzle for you guys from Connections from the 1970s. So remember, this is a series that has to do with the story of technology, where do ideas for technology come from? Sometimes these stories elapse over hundreds of years. Can you guys figure out what technology he's talking about here?
And that's what happened in this case. In 1820, a rather dull Dane called Ørsted was teaching his students that an electric current going down a wire shouldn't have any effect whatsoever on a compass needle.
Hey, isn't that the story Paul Hewitt was telling you guys yesterday? Ørsted was teaching his class saying, oh, electricity, magnetism has nothing to do with each other. And then what did he find? It did have something to do with it.
A rather dull Dane called Ørsted was teaching his students that an electric current going down a wire shouldn't have any effect whatsoever on a compass needle. When, to his utter chagrin, it did. Well, no fool he. Ørsted immediately made it known that if an electric current going down a wire caused a compass needle to swing, it had to be generating a magnetic field and moving the needle. Poor old Ørsted. I mean, who's ever heard of him? Michelangelo, yes. Ørsted? And yet, the fact that an electric current generates a magnetic field is fundamental to the way the world is run today. I mean, take just one thing that happened because of Ørsted. If you wind a live wire round and round a bit of iron, the magnetic field generated by the current causes the iron to become a magnet, an electromagnet. Now, somebody did that in England in 1825. In 1857, a German took a tuning fork and put it next to an electromagnet, turned it on and off, turned the magnetic field on and off, and caused the tuning fork to vibrate. And then in 1870, a Frenchman living in America took a diaphragm, put a bristle on the end of it, and then yelled into the diaphragm to make it vibrate. And the bristle jiggled up and down and made a pattern on smoked glass. And the pattern was always the same for the same word. Now, I say all this because the brilliant invention that came out of it, and it was a brilliant invention, was really no more than putting all those bits and pieces together.
So what technology did all those bits and pieces lead to? If you put them all together, you get a what? Ooh, okay, that's good, guys. That's pretty close to what we're getting to. Right, you got to guess for a record player. Right, looking for something a little different, but okay, radio. That's right in the ballpark. Right, here, I'm going to rewind. Here, guys, watch these clues again. Telephone. That's it. Telephone. Yeah. So on one end you have a speaker. On the other end you have a microphone. Those are some earlier guesses today. And actually, if you put those two together, a speaker and a microphone and a wire to connect it. Right? Here. So let's see this play out.
The bristle jiggled up and down and made a pattern on smoked glass. And the pattern was always the same for the same word. Now, I say all this because the brilliant invention that came out of it, and it was a brilliant invention, was really no more than putting all those bits and pieces together. Like this. You yell into that cone. That causes a metal diaphragm here to vibrate. Now, that metal diaphragm is within this magnetic field, and as it vibrates, it kind of drains it, causing the current in the live wire to fluctuate. This fluctuating current fluctuates along a wire until it reaches an identical setup, where because it's a fluctuating current, it makes a fluctuating magnetic field. And that causes another metal diaphragm to vibrate in exactly the same pattern as the first one. And when it does that, it makes a noise in that cone. So what you yell in here comes out there.
So there's a little more to say on that, but that's yeah, that's just it. There you go. There's telephone right there. And one of the components was electromagnet, which is one of the things you guys make today. So we're working towards that. But I got some other things need to clean up, some other details. Take a picture. So talk about Faraday cage a little bit. Let's say you guys know we're in Florida. I think lightning capital of the world. I think right. And so let's say you're out in a big old cow pasture in Florida, and then a big old storm rolls in. Ooh, look at the storm clouds. Zeus is getting mad today. He's throwing some lightning your way. Now, big old field. Is that a good place to be? You want to be in a big old field during a lightning storm? So let's go with no, because if you're walking around vertical, aren't you a giant pointy object? And this electricity says, oh, what's the path of least resistance to get to the ground? Hey, that guy right there. But let's say there's a couple of buildings out in this cow pasture with nothing else around, a couple of buildings. They're old, abandoned, maybe they've been here since 1920. And okay, the doors are open to both of these. But you notice there's a difference between these two buildings. One of these buildings is framed with wood, and the other building is framed with steel. Okay. And you're thinking, okay, well, I don't want to be running around this open field. I got to get inside. I got to get indoors. Now, which building do you want to pick? Let me see you show of hands. Do you want to go inside the wood building or the steel building? Show of hands for, you guys, everyone here? Right, show of hands for wood. Who's going to run inside the wood building? Who wants to run inside the wood building? Got some votes there. Who wants to run inside the steel building? Steel building. Got some votes there too. I'm putting my vote on the steel building. I'm running inside the steel building. Okay. Here's why. Oh, let's say this lightning is hitting both the buildings. Okay. So when it hits the steel building, okay. Oh, what's the path of least resistance for the electricity to get into the ground where it wants to go? Would it be the steel frame? Right around the steel frame? Okay. And you're safe inside. That's called a Faraday cage. Okay. But what if you had chosen the wood building and the lightning hits this wood frame? Now, what might possibly be the path of least resistance to get to the ground might go through you, which wouldn't be as good. Back. Oh, here, let's show you guys a picture of this in action. Got a picture. Oh, Faraday cage. You guys see that kid in that metal frame? It has to be a metal frame. You think it's a metal frame because we're zapping that with electricity. And the path of least resistance is the metal frame. As long as the kid just stays right in the center, he's perfectly fine. Okay. Faraday cage. It's a Faraday cage right there. Okay. Now, back in Ben Franklin days, when people were just figuring out how electricity works, guys, what buildings do you think were made out of wood and had a point on the top, made out of wood? That would be a what kind of building? Probably a church, maybe. Right? Churches all the time got fried by lightning. Right? And Ben Franklin invented something called a lightning rod. He said, hey, what if I take a metal rod and put it up here? Because it used to be just like a wooden steeple, right? But what if I have a metal rod and I run a wire all the way down to the ground? Right? Now, if lightning is nearby, it's most likely to hit that metal rod, and it's just going to fall right down to the ground and not really interact with the wood so much. And it's saved a lot of churches from being burned down. Right? Now, the natural extension from that is, well, why not just have the whole building framed with steel? So that if this lightning hits any building that's framed with steel, then it'll necessarily just follow that frame down to the ground, which is exactly what we're sitting in right now. You guys think that all modern buildings have these steel frames? Like especially in Florida, but probably really anywhere. Okay. So in the case of a lightning storm, you're safe indoors, metal frame, the lightning follows that metal frame down to the ground. All right, Faraday cage. Okay. Ooh, Tesla coil. Have another demo for you guys. You guys remember last week that Van de Graaff generator? You guys remember that? Okay, so here's the alternating current version of this, because the Van de Graaff was a static charge, like DC, but this is going to be alternating current. I do have to plug this in. So I plug this in right here. And here, you guys can hear it. See that? Right. Now, if I let's go on enough, you might see a spark come out here, maybe. Let's see if I can get a spark. Yeah, I don't know if it's showing up on camera, but it's in front of me. So you can see it in person. But you know what you can see on camera is I have a fluorescent bulb right here. And so guys, watch this. I turn. Did I just grab my camera? What just happened? Yeah, we're gonna put a pause on this video and see what just happened here. And we're back. We're back. Okay, so let's try this now. Okay, you guys see this fluorescent bulb? Watch this. You see that? Okay, so because it's exciting ions inside the fluorescent light, creating a plasma right there. Is that too? All right, so here, put this seconds safe case there. All right, so guys, later in class today, I'm just put this Tesla coil back in the lab area, and if you guys want to play around with that, you get a little shock from that too, just like with the Van de Graaff generator. Is it? Because you guys have some time. All right, so that's all these three right here. All right, so you guys get with all that. Our main lab today is you guys going to build each of these. Now, these I constructed yesterday. I'll remind you guys how to do these today. Here's what we're doing the rest of the week, just to knock these out. Next couple of days, I want to do a little bit of astronomy with you guys. I really pull up some crash course videos and have you guys follow along on a page, but at least I'll get some astronomy in. So I selected 8 videos. I think it works pretty well. And if this really intrigues you, if you really like astronomy, of course, there's more crash course videos like the ones you'll be able to see tomorrow. So you guys can find those on your own time. Or we also have an astronomy class been going for first time this year. Right, and then how are you guys going to dress for Friday? For outside. So outside activity on Friday. We're going to be doing an orienteering activity on Friday. Right, so dress ready to go outside. All right, so main lab today, right here. Yesterday, I built for you guys a compass, electromagnet, motor. I'll remind you guys how to do that. You guys have a couple of cups on your desk, and one of them has some water in it. Okay? And then you can put the dry cup inside the wet cup, so it's like free to rotate. Okay? And then you guys have a stack of these bar magnets. Now, I found an ideal number of magnets to make the compass work is 3. Right? Remember, if you have one bar magnet and you stick more bar magnets to it, it effectively makes one giant magnet. But it's really 3 individual bar magnets. And you also have to know where the poles are on these magnets. Because who remembers from yesterday? Where are the poles on these magnets? Is one of the poles could be this space right here. This might be the North Pole or the South. And this other side could be either the South or the North. Right? Now, I don't know which one's which, but you can find out by putting the compass together. Okay. Guys, how do you want to align the poles for the compass? Do you want to align the poles vertical up down or horizontal side to side? Yeah, horizontal side to side. Right, so you put these magnets in here, and then, well, I don't have water in the cup, but if I did, this would naturally, just like yesterday, this would naturally align to Earth's north-south field, which would probably look about like that. So I think that way's south and that way's north, basically. This should align with Earth's magnetic field. Right, so you guys got compass? Right. Electromagnet, like you guys saw, James Burke was referring to electromagnet as part of the original telephone. Right? All you need is a bolt, a coil of wire you can go around. You probably have these materials from earlier classes. You guys got these. Okay. Now, you do not need a permanent magnet. Notice there's no permanent magnet in the frame right now. All you need is coil wires, bolt, and a battery. Okay? And then this should be able to pick up something ferromagnetic like this paper clip. Let's see if it does. Can I pick up this paper clip? Oh, look at that. It picks up the paper clip. You guys see that? Until I disconnect the battery. And then it loses all its magnetic properties. Oh no, I can't pick it up anymore. Right. So you guys see that? Let me speak of stripping these wires. Stripping these wires. You guys see how the wire strip right here? Right. If you need any more materials, let me know. Like if you need a new battery, I don't think you will because I have this battery tester. Guys, look at this battery tester. That's this little tool. So you guys see that needle moves to the green part and it says good. So green is good. So this one's still charged. This one's good. I checked them all earlier today. So your battery should be good. If you're not sure about that, let me know. Again, check that with you guys. Okay. And then wire. You probably have all the wire you need, but if you need new wire, let me know. I can get you guys the new wire. Okay. You might need to strip the ends. Guys, everybody look up here. Everybody look up here. This is a safety thing. You guys tell me, what's the correct way to strip the wire? Should I do this? Should I put the scissors here and go like, Should I do that? The correct answer is no, I should not do that. Because there's a lot of resistance building up. You have no control. These big, heavy blades go flying. Your friend's eyeballs are nearby. It's a bad combination. Right. But should I do this instead? What if I wanted to extend this lead a little bit? Could I very carefully make an incision all the way around? Very careful, very careful, very careful. I only cut the insulation, not the wire itself. Then I put the scissors to the side. I'm done with the scissors. Then I can just flip this insulation right off. You guys see it slips right off? Is that easy? Look at that, that easy. You see that? Right. You guys can do that if you have to strip the insulation off the wire. Right. And finally, motor. Now this one's the trickiest one. So there's some features you're looking for in this motor. You guys see it's a coil of wires and the leads are stripped. And I show you guys how to properly strip the wires. Right, if you have any questions, definitely ask me. It's a safety thing. Right? Now, one thing you're looking for. Do you guys see how? Now, here's a detail that lots of students have missed over the years, but you guys are going to miss it because I'm going to point out right now. Guys, if I draw a line between these two leads, do you guys see how the line goes through the center of the circle? You see that? If I draw a line between those two leads, see how it goes through the center of the circle? Okay. That's an important feature to make this work because that means it's going to be balanced. So if I balance this on my fingers, you guys see that just like that? It doesn't really have a strong preference for orientation, whether it's like this or like this, right? Versus, I'm going to show you guys a counterexample. You guys see this guy right here? You guys see this one? Right? If you hang this on the leads of the paper clips, you guys see how it always wants to hang down like that? Right? And that's no good because it would take an enormous amount of energy to make this rotate all the way around, and it would also run out of space. So that's not going to go all the way around. But this will, right? And I can show you that right here. Right? Now this one, like I said, this is the trickiest one to get working today. You have to get a lot of things like subtly correct to get clear this up. So I got a stack of magnets here. Stack of magnets. Leave this in the middle. I have one of the poles straight up, vertical. Take a couple of paper clips, attach them to the battery. Now I'm just going to hold these in place. You guys do have a roll of tape today that can help hold your motor together. Like my motor does have some tape on it. Right? If you want to tape the paper clips on the battery, that's okay too. Right? And this is really subtle. Do you guys see how my paper clip on the cathode is connected to the side of that knob right there? Right? Used to be right there. And then on the anode side, see this paper clip? I want it to be right in the middle of the flat side. Right? If it's shifted off like this, it's not going to connect. It's not going to make the current. Right? So I need that connection right there. Right? I want the metal to touch the metal. Do you guys see how this, like if I slide this over, guys, if that paper clip is touching that insulation, is that going to send a current through? No. You need the metal to touch the metal. Right? Metal. Right? Then put this all together. If it's making a connection, it might even get hot. Right? And put this near my stack of bar magnets and it was going. Okay, try it again. Sometimes this takes it a couple times. Oh, it just, well, it didn't until it did. Reset this thing. Okay. It's like it works and then it's, there it goes. Guys, and how long did that spend for? Yeah, until the battery runs out. There it goes. Look at it go. Because that's where it's getting its energy from. It's getting it from the chemical bonds in the battery. Look at there. So, okay, took me a couple of tries. Right. Probably the same thing for you guys. A couple of tries. Okay. All right, so is there any question about what you're doing today or anything for the rest of this week? Okay. All right, so I will walk around, help you guys out. And remember too, I'm going to put the Tesla coil back in the lab area. So if you want to play around with the Tesla coil too. All right, and then I will give you guys some points in the grade book when I see you guys make each of those 3 devices right there.